Something left the sun yesterday, and it picked the worst possible moment to leave. A coronal mass ejection, a wave of plasma and magnetic fury, is currently racing toward Earth at over 1,200 kilometers per second. It will arrive on March 19th, one day before the spring equinox. That timing is not poetic coincidence. There is a little-known geophysical effect that drops Earth's magnetic defenses to their annual low point every single spring, and this storm is arriving right into that window, slamming into a magnetosphere already bruised from last week's hit. And in 2 weeks, 4 astronauts are scheduled to leave the only magnetic shelter we have. This is the story of why this solar storm is different from the others, why the timing is not just bad but geometrically terrible, and what it means for 4 humans about to step outside Earth's defenses entirely. If this has you hooked, subscribe to the Skylab because the sun is not finished with us yet, and we intend to watch every eruption, every CME, every reminder that we are completely at the mercy of our solar system. Drop a comment below and tell me your honest opinion. Is a CME hitting Earth's magnetic weak point during the most active solar cycle in memory pure coincidence, or a deliberate pattern we're only beginning to pay attention to? Now, let's get into it. Part 1. The Earth-bound CME is real, and it's arriving at the worst possible moment. Something left the sun yesterday, and it is heading straight for us. At 12:15 UTC on March 16th, 2026, a sunspot region called Active Region 4392, a large tangled knot of magnetic energy sitting dead center on the solar disk, erupted. The flare it produced was classified as M2.7, moderate on the official scale. The kind of event that solar physicists note in their logs and move on from, except this one didn't move on, this one moved toward us. The associated coronal mass ejection, a bubble of magnetized plasma roughly the size of several Earths, launched outward at approximately 1,227 kilometers per second. That is not a slow crawl, that is a solar cannonball. Let me put that speed in perspective for you. The distance from Earth to the Moon is about 384,000 kilometers. This CME would cross that gap in roughly 5 minutes. It is racing across the 150 million kilometers between the Sun and our planet, and forecasters are tracking it with growing attention. Predicted arrival, March 19th, 2026. Which brings us to the part of this story that transforms a moderately interesting solar event into something that deserves your full undivided attention. March 19th is one day before the spring equinox. Now, I know what you might be thinking. The equinox is an astronomical milestone, the moment when day and night are equal, when the sun crosses the celestial equator, when people plant gardens and celebrate fresh starts. It sounds like the least threatening date on the calendar. And yet, buried in decades of geophysical research, there is a mechanism, a real, documented, peer-reviewed mechanism that makes Earth's magnetic defenses measurably weaker around the equinoxes than at any other time of year. It is called the Russell-McFerrin effect, and we're going to talk about it in depth shortly. But for now, just hold on to this. The CME is not arriving at a random time. It is arriving during a window when our planet's magnetic shield is, by geometry and physics, at its most open. A coronal mass ejection is not like sunlight. Sunlight is a stream of photons, massless particles travelling at the speed of light, reaching your skin as warmth. A CME is something categorically different. Imagine, if you will, a tsunami versus a gentle tide. Sunlight is the tide, constant, predictable, benign in ordinary doses. A CME is the tsunami. It is a massive eruption of plasma and magnetic field that peels away from the sun's outer atmosphere and tears across interplanetary space, carrying with it billions of tons of charged particles and a magnetic field that can interact violently with Earth's own. When that magnetic field arrives with a southward orientation, meaning its field lines point opposite to Earth's, something extraordinary happens. The two magnetic fields connect, they tear open, energy floods into the magnetosphere, currents strengthen, particles accelerate, and the aurora that paints the sky is just the beautiful face of something that, at its most intense, can induce currents in power lines, confuse GPS systems, and silently fry the electronics buried inside satellites that the modern world depends on without ever thinking about. This CME originated from active region 4392, a sunspot group that has been described by solar physicists as large and magnetically complex. It is currently facing Earth, which means any eruption it produces, any flare, any new ejection has a direct line to our doorstep. And here is where the story gets a second layer of unease. That region has not gone quiet. As of the time this script was written, forecasters were assigning a non-trivial probability, around 5%, for an X-class flare in the coming 24 to 48 hours. 5% might sound small, but 5% of an event that can trigger the most severe category of geomagnetic storms is not a number you dismiss. It is a number you watch. We also know this is not the first disturbance Earth has absorbed this week. A coronal hole stream, a relatively steady, high-speed wind blowing from an open region on the Sun's surface, drove a G2 geomagnetic storm on March 13th and 14th. The magnetosphere absorbed that hit. It has not fully recovered. The radiation belts, the zones of energetic particles trapped around Earth by magnetic fields, are already elevated above alert thresholds. We're not going into this CME from a position of calm. We're going into it already rattled. And there is one more detail. In approximately 2 weeks, 4 human beings are scheduled to climb into a spacecraft called Orion and travel beyond Earth's magnetosphere as part of NASA's Artemis II mission. They would be leaving the only magnetic shield we have at the peak of a solar cycle that has already outperformed nearly every prediction made for it. Whether that mission proceeds on schedule, what its planners know about the current solar environment, and what it means for humans to travel through deep space during a period like this, that is a thread we will pull in full later. For now, hold this image in your mind. A billion-ton wave of magnetized plasma, moving at over 1,000 kilometers per second, aimed at a planet whose magnetic defenses are about to hit their annual low point, arriving into a system that is already stressed by last week's storm, fired from a sunspot that hasn't finished with us yet. The sun picked its moment, and the question you should be asking yourself right now is, why does the equinox change everything? Part 2. Why the Russell-McFerran effect isn't just academic. There is a pattern in the data that took scientists decades to fully explain. If you were to plot geomagnetic storm activity across an entire year, mapping out every disturbance, every elevated index, every moment when Earth's magnetic environment went haywire, you would notice something that should not, on the surface, make any sense. The worst storms cluster around spring and fall, not around the periods of peak solar activity, not randomly, around the equinoxes. It is a semi-annual rhythm hidden inside solar chaos, and its explanation is one of the most elegant and underappreciated concepts in all of space weather science. The Russell-McFerran effect is named after Christopher Russell and Robert McFerran, who first described it formally in 1973. Their insight was geometrical. Earth orbits the Sun at a tilt. Our axis is inclined about 23.5 degrees relative to the plane of the solar system. That tilt is why we have seasons. But it also means that throughout the year, the orientation of Earth's magnetic field relative to the solar wind changes. And at the equinoxes, that orientation reaches a very particular alignment, one that makes it dramatically easier for the solar magnetic field to connect with Earth's. Here is the metaphor that makes this click. Imagine Earth's magnetic field as a force field, a bubble of invisible influence that deflects the solar wind the way a curved windshield deflects rain. Most of the time, that deflection works because the magnetic fields of the solar wind and Earth are oriented in opposite directions. Opposite poles repel. The solar wind gets pushed aside, but magnetic reconnection, the violent process that lets solar energy pour into Earth's system, happens when the incoming field points south, opposite to Earth's northward field at the day side. That is when the two fields can link, reconnect, and rip open the door. At the equinoxes, Earth's axial tilt causes the geometry of the interaction to favour that southward connection. The angle of Earth's magnetic dipole relative to the incoming solar wind is arranged, for a few weeks around March and September, in a way that makes reconnection more efficient. The door is not locked, it is ajar. And any CME carrying a southward magnetic field component called negative BZ finds it dramatically easier to punch through than it would in June or December. This is not fringe science. This is not a theory championed by someone posting about planetary alignments on social media. Scientists have validated this pattern across multiple solar cycles using ground-based magnetometer networks spacecraft data, and decades of storm records. The semi-annual variation in geomagnetic activity is one of the most robustly reproduced findings in space weather research. And yet, outside of the field, almost nobody knows about it. Think about what that means for this specific CME. We have a fast-moving ejection, launched at over 1,200 kilometers per second, arriving on March 19th. The spring equinox is March 20th. The CME is not arriving a month before the equinox, or a month after. It is arriving within hours of the exact window when Earth's magnetic geometry is most favourable to disruption. That is the kind of coincidence that a thriller novelist would be accused of over-engineering. The practical consequence of this is real. A storm that might register as a G2 event under ordinary conditions, moderate, manageable, largely invisible to most people, can behave more intensely under equinox conditions because the magnetosphere is more receptive to energy injection. The ring current, a belt of charged particles circling Earth, can be driven to higher intensities. The aurora can appear at far lower latitudes, and critically, the induced currents on the ground, in power lines and pipelines, can be stronger than standard storm-level forecasts would suggest. You might be wondering, if scientists have known about this since 1973, why are our infrastructure systems not already designed around it? And that is a very good question. Some are, in principle. Grid operators in northern latitudes have contingency protocols. Satellite operators have safe modes. But the full integration of space weather into civilian infrastructure planning is, to put it charitably, still a work in progress. The Russell-McFerran effect is a calendar fact that the entire power grid sector should have tattooed on its scheduling board. Many do not. There is a compounding factor that makes the equinox vulnerability even sharper this time. The magnetosphere arriving at this CME is not at baseline. It absorbed a storm from a coronal hole stream earlier this week. It is carrying residual stress. The ring current is not neutral. The radiation belts are already agitated. And now, into that pre-disturbed system, at the most geometrically vulnerable moment of the year, a fast-moving CME is about to arrive. A G2 storm through an ordinary magnetic shield in midsummer might barely make headlines. The same storm, arriving in a stressed magnetosphere during equinox geometry, could produce effects that exceed what the storm classification alone would suggest. And this is where the science gets genuinely uncertain, because compounding storm effects, stacked impacts on a magnetosphere that hasn't recovered, are one of the least well understood areas in space weather research. So what happens when you hit something that's already rattled? That is exactly what we need to talk about next. Part 3. The double hit problem, storming into a magnetosphere that never recovered. Scientists have a term for what Earth's magnetic environment looks like right now, and it is not reassuring. On March 13th and 14th, 2026, a stream of high-speed solar wind blowing from a coronal hole on the Sun's surface reached Earth and drove a G2 geomagnetic storm. A coronal hole is an open region in the Sun's magnetic field, a zone where the field lines stretch outward into space instead of looping back to the surface, allowing solar wind to escape at unusually high speeds. These streams are relatively steady and predictable compared to CMEs, but they are far from harmless. The stream that hit Earth last week pushed the planetary K-index, a measure of geomagnetic disturbance, into disturbed territory and energized the radiation belts. The magnetosphere, after absorbing that impact, needs time to recover. Think of it like a shock absorber. Hit it once, hard, and it compresses. Given enough time, typically several days, sometimes more than a week, the ring current dissipates, the plasmasphere refills, the radiation belt populations relax back toward quieter levels. But that recovery takes time, and that time has not been given. Less than a week after the coronal hole stream subsided, a CME is inbound. The shock absorber has not extended back to its resting position. Another hit is coming. This is what space weather researchers call a compound storm sequence, and it is one of the most understudied areas in the field. We understand individual geomagnetic storms with reasonable sophistication. We can model ring current evolution, trace particle populations through the magnetosphere, and forecast the decay of a disturbance after a single event. What we do not have is a mature, validated framework for what happens when storms stack. When the second CME arrives into a magnetosphere that is still reverberating from the first, the concern is not merely additive, it is potentially nonlinear. Residual current systems left by the first storm can interact with the driving forces of the second in ways that amplify the total effect beyond what you would expect from simply adding two storms together. Some researchers have proposed that under compound conditions, the ring current enhancement, the intensification of that belt of charged particles circling Earth, can exceed what the individual storm drivers would produce in isolation. We're talking about emergent behaviour, where the whole is more disruptive than the sum of its parts. There is also the matter of the Van Allen radiation belts. These are two concentric zones of energetically charged particles, mostly electrons and protons, trapped by Earth's magnetic field. They fluctuate enormously with solar activity. During quiet times, they are relatively predictable. During geomagnetic storms, they can be dramatically energized, with electrons accelerated to energies measured in millions of electron volts. Those high-energy electrons, above roughly 2 million electron volts, are a specific, serious problem for satellites. The radiation belts have been elevated above alert threshold since the coronal hole event earlier this week. That means energetic electrons are already circulating at elevated levels. When the CME shock arrives, it can act as an impulsive accelerator, kicking those already elevated populations to even higher energies. The result is an environment that exceeds what you would expect from the CME alone, because you are starting from an already elevated baseline. High-energy electrons do something insidious to satellites called deep dielectric charging. The electrons are energetic enough to penetrate the outer shielding of a spacecraft, the metal walls that protect against lower energy particles, and instead of stopping at the surface, they bury themselves inside the insulating materials used in electronic components. Over hours or days, charge accumulates in those insulators. When the charge reaches a critical threshold, it discharges, suddenly, unpredictably, producing a burst of current that can destroy components, flip memory bits, or trigger anomalous behavior in ways that are nearly impossible to trace from the ground. Satellite operators call these anomalies. The public never hears about most of them. A navigation satellite briefly producing inaccurate position data, a communications transponder that needs to be power cycled, a scientific instrument that goes into safe mode during a storm and loses hours of data. These are the invisible casualties of space weather, happening silently in orbit, while most people below are entirely unaware that anything unusual is happening in the sky. The infrastructure we depend on is extraordinarily space-dependent. The timing signals that synchronize global financial transactions travel through GPS satellites. The weather forecasts that tell farmers when to plant, that guide air traffic controllers, that warn coastal communities about incoming hurricanes, they depend on a constellation of orbiting sensors whose health is directly tied to the radiation environment. When that environment is stressed, and when the stress is compounding from one event into the next before recovery is possible, the risk to that infrastructure is not theoretical, it is operational. Right now, the radiation belts are already agitated, the magnetosphere is still absorbing the effects of last week's coronal hole storm, and a fast-moving CME arriving into this preconditioned system during the equinox vulnerability window is scheduled to make contact on March 19th. The conditions for a compound disruption, worse than the individual event classifications would suggest, are all present simultaneously. And remember, the sunspot region that fired this CME is still active, still aimed at Earth, and still carries the potential for something larger. Which means the question is not just what this CME does on its own, the question is what it does as the opening act, because active region 4392 may not be finished with us. Part 4, AR439, 2, active, directed at Earth, and still capable of something bigger. The sunspot that started this is not done staring at us. Active region 4392 is classified as a large, magnetically complex sunspot group, and its current position on the solar disk means it has a nearly direct line to Earth for the next several days. In solar physics, location matters enormously. A powerful flare erupting from the solar limb, the edge of the visible disk, sends most of its CME sideways, off into interplanetary space, largely missing Earth. But active region 4392 is not at the limb. It is not even close. It is facing us. Every eruption it produces has us in its crosshairs. Sunspot regions are classified by the complexity of their magnetic structure. The simplest regions, called beta regions, have a straightforward arrangement of opposing polarities, somewhat like a bar magnet. These can produce flares, but they are generally less productive. More complex are gamma and delta regions, where the opposing magnetic polarities are intermingled in the same sunspot group, tightly wound magnetic fields storing enormous amounts of energy. When that stored energy releases, it releases explosively. Active region 4392 falls toward the more complex end of this spectrum, and its track record this week has already demonstrated it is willing to fire. The flare classification system runs from A to B to C to M to X, with each letter representing roughly a tenfold increase in X-ray output. C-class flares are common during solar maximum. They happen frequently and produce minimal impact. M-class flares, like the M2.7 that launched this CME, are moderate events. They can cause shortwave radio blackouts on the day side of Earth, affect high-frequency communications used by aviators and emergency services, and when they produce CMEs, they are significant events worth monitoring. X-class flares are the heavy hitters. The largest X-class events produce radiation burst powerful enough to cause immediate radio blackouts across entire hemispheres, and the CMEs they launch are often faster, more energetic, and more capable of driving severe geomagnetic storms. Forecasters have assigned approximately a 5% probability of an X-class flare from active region 4392 within the next 24 to 48 hours. On any normal news day, a 5% probability generates a one-line mention in a space weather bulletin and nothing more. But context transforms that number. The CME launched by the M2.7 flare is already in transit. If an X-class flare erupts before that CME arrives, which could happen as early as later today, it could launch a second, faster CME. A second CME moving faster than the first can overtake it in space, merging with it in a phenomenon researchers call a CME-CME interaction, producing a combined magnetic structure that is often more geoeffective, more damaging to Earth's magnetic field than either CME would have been individually. This scenario has a name in the literature, a cannibalistic CME event, where the trailing eruption essentially consumes and merges with the leading one. The resulting merge structure arrives at Earth with enhanced magnetic field strength, higher dynamic pressure, and unpredictable internal structure. Forecasting the magnetic orientation of a merged CME, that critical BZ component which determines whether the CME's field will reconnect with Earth's, becomes significantly harder. The uncertainty balloons. The potential for a severe rather than moderate geomagnetic storm increases substantially. Solar cycle 25, the current solar cycle, has consistently outperformed the predictions made for it before it began. Long-range forecasting by the Solar Cycle Prediction Panel suggested a relatively moderate peak. Instead, the cycle has delivered elevated flare counts, multiple periods of high activity, and a solar maximum that has lingered longer and reached higher than expected. Active region 4392 is, in some ways, emblematic of this cycle's character. Larger than average, more complex than typical, and positioned to do maximum damage during a period of already elevated baseline activity. There is also a more speculative scenario worth mentioning, and I want to be clear that this is speculative. Some researchers have described the concept of sympathetic eruptions, where one CME, in releasing tension from the magnetic field on one part of the Sun, triggers a cascade of eruptions from adjacent regions. The Sun's magnetic field is a globally connected structure. A large eruption from one region can cause ripples, disturbances that travel across the solar surface and potentially destabilize neighboring regions. Whether active region 4392's eruption earlier this week has set off any such cascade is not confirmed, but the possibility deserves acknowledgement when discussing a region that is still active, still loaded, and still pointed directly at Earth. The first CME is already airborne, the region that fired it has not gone quiet, and in roughly 72 hours that CME will make contact with a magnetosphere carrying the scars of last week's storm and the vulnerabilities of equinox geometry. But there is an even larger picture here, one that requires us to zoom out from this single week and ask a question that the data has been quietly raising for the past 2 years. Is this week unusual, or is this what the new normal looks like? Part 5. The big realization: this is not normal solar weather. We have been here before, but not quite like this. Solar physicists use a numbering system to track the Sun's activity cycles, roughly 11-year periods during which sunspot activity rises to a peak and falls back to a minimum. The cycle we are currently in is solar cycle 25. Before it began, the Solar Cycle Prediction Panel, a group of expert scientists whose job is to forecast the behaviour of the next cycle, issued a prediction. The forecast called for a relatively modest peak, a quiet cycle, the kind of solar maximum that would keep space weather forecasters employed but not particularly alarmed. That forecast was wrong, not slightly wrong, substantially wrong. Solar Cycle 25 has delivered more M-class and X-class flares than predicted. It has produced multiple strong geomagnetic storms at a higher frequency than the pre-cycle model suggested. The solar maximum, the peak of activity, appears to be both stronger and more prolonged than anticipated. Active Region 4392 is not an isolated anomaly in an otherwise quiet sun. It is one of dozens of complex energetic sunspot regions that have characterized this cycle's unexpectedly robust behavior. Why does this matter beyond the immediate event? It matters because our infrastructure planning, our satellite insurance models, our grid protection protocols, all of them are calibrated at some level to historical expectations about how active the sun should be. If those expectations have been systematically underestimating solar activity for this cycle, then our preparedness baseline is calibrated to the wrong sun. Historical precedent offers instructive context. In March of 1989, a geomagnetic storm driven by a powerful solar eruption struck Earth. The Quebec power grid, operated by Hydro-Quebec, collapsed entirely. 6 million people lost power for approximately 9 hours. Transformers were damaged. The storm was not the most extreme event ever recorded. It was a severe but not unprecedented geomagnetic event. Yet it caused cascading, systemic failure of a major power grid in a modern, industrialized country. The reason is that electrical grids were never designed to be resilient against geomagnetically induced currents, the slow, powerful surges of electricity that solar storms drive through the ground and into power infrastructure. The March 1989 event was a G4 to G5 storm, powerful, but not in the category of the Carrington event of 1859, which was almost certainly the largest geomagnetic storm in recorded history. The Carrington event produced auroras visible at the equator, induced currents that set telegraph offices on fire, and reportedly allowed some telegraph operators to continue sending messages even after disconnecting from power, using the geomagnetic current alone. If a Carrington-level event struck today, the effects on satellite infrastructure, power grids, and communications networks would be staggering. This current CME is not a Carrington event. That needs to be stated clearly and without hedging. The M2.7 flare and its associated CME are not, on their own, in the category of civilization-threatening space weather. But the pattern surrounding this event, the stacked storms, the elevated radiation environment, the equinox vulnerability, the active and still-firing sunspot region, the context of a solar cycle that has outperformed predictions, that pattern is what deserves attention. Not as cause for panic, but as a signal that our collective attention to space weather resilience is overdue. There is a concept in complex systems science called emergent risk, hazards that arise not from any single factor, but from the combination of multiple factors simultaneously interacting in ways that no single model captures. The current situation has several such factors: an already disturbed magnetosphere, equinox geometry, a fast CME, an active source region, and an elevated radiation belt. None of those alone would be unusual. All of them together create a risk profile that is qualitatively different from the sum of its parts. Space weather is not a niche concern for satellite operators and aurora photographers. It is a civilizational infrastructure issue, one that affects the power you use to read this, the signals that guide the plane you board, the timing systems that make financial markets function, and the communication networks that emergency responders depend on. And understanding why this week is different from an average week is the first step toward understanding why, as a civilization, we are considerably less prepared for this than we should be. But the story of this CME and what it means for the next few days is only part of the picture, because waiting just beyond the reach of Earth's magnetic shield, about 2 weeks from now, 4 astronauts are preparing to leave that shield entirely. And what they would be flying into is exactly what we have been describing. Just Cercourt. Part 6. The Science. Uncertainty. What happens when geomagnetic conditions stack? Science is remarkably good at describing one thing at a time. Two things simultaneously is where it starts to sweat. We have well-developed models for how a single CME interacts with Earth's magnetosphere. Decades of spacecraft measurements, ground-based observations, and theoretical modelling have given us a reasonably mature understanding of the ring current, that donut-shaped belt of charged particles that forms and intensifies during geomagnetic storms, and how it evolves after a single impact. We know roughly how long it takes for the ring current to decay after a storm. We know the typical timescales for plasmaspheric refueling, the process by which the inner magnetosphere replenishes the cold, dense plasma that storms strip away. These are well-characterized processes, and our models handle them with confidence. What happens when a second storm arrives before those processes complete? That is where the models start to hedge. Magnetospheric recovery is not a simple linear process. The ring current does not simply drain like water out of a bathtub. It decays through a combination of charge exchange, wave-particle interactions, and outflow through the magnetotail, and each of those mechanisms operates on different timescales and is sensitive to the prevailing conditions in the magnetosphere. A ring current that has been partially energized but not yet fully dissipated when a second CME arrives is starting from a non-equilibrium state. The incoming energy from the second storm does not encounter a blank slate. It encounters a system that is mid-transition, with existing current systems, elevated particle populations, and altered plasma distributions. Under these conditions, researchers have hypothesized several possibilities. One is that the second storm is amplified, that the pre-existing ring current acts as a seed that the new energy input can build upon more efficiently, driving the ring current to higher intensities than the second storm would achieve on its own. Another possibility is partial interference, that the pre-existing current systems interact with the new driving forces in ways that redirect energy into unexpected channels, potentially enhancing particle precipitation into the atmosphere or driving stronger field-aligned currents in regions that would not normally be affected. A third, less studied possibility is that the stacking reduces the effective penetration of solar wind energy, that a preconditioned magnetosphere in some configurations is actually less geo-effective, not more. The honest answer is that the data on compound storm sequences is sparse, the models are underdeveloped, and the scientific community does not have consensus on which of these scenarios dominates under which conditions. What we do have is historical case studies, and they are instructive if not conclusive. There have been periods, most notably during solar cycle 23 in the early 2000s, when clusters of CMEs struck Earth in quick succession, producing storm sequences where the cumulative geomagnetic disturbance clearly exceeded what individual storm models would have predicted. The so-called Halloween storms of October and November 2003 produced back-to-back severe and extreme geomagnetic events that satellite operators described as some of the most anomaly-prone periods they had recorded. Several satellites experienced deep dielectric charging anomalies. GPS accuracy degraded significantly. Radiation belt electron flux reached record levels in some energy ranges. The current situation is not yet at Halloween storm intensity, but the structural similarity, a sequence of events arriving into a magnetosphere that has not recovered during an active period of the solar cycle, with an energized radiation environment, shares features that should make space weather scientists pay close attention. And there is an additional factor that elevates the scientific uncertainty in this case: the equinox geometry, which modifies the efficiency of solar wind coupling to the magnetosphere in ways that our storm models handle imperfectly. The Russell-McFerran effect is well established as a statistical pattern but is not yet fully integrated into real-time storm forecasting models in a way that accounts for its amplifying effect on compound events. This means that the official storm forecast for this CME arrival, almost certainly G2, possibly G3, may be conservative. Not because the forecasters are incompetent, but because the compounding factors present in this event are precisely the factors that push events beyond what nominal models predict. The formal uncertainty intervals around those forecasts are wide, and wide uncertainty, in space weather as in any domain of risk, means that the tails of the distribution, the worse than expected outcomes, are more probable than a single central forecast number communicates. This is the honest scientific picture. We are watching a real-time case study in stacked geomagnetic interactions, the outcome of which carries more uncertainty than the clean numbers in a forecast bulletin suggest. And somewhere above us, right now, satellite operators are watching the same data and quietly hoping the uncertainty resolves toward the calm end of the range. It may not. And knowing why this week sits inside a much longer and stranger history of solar behaviour is essential to understanding what we might be witnessing. Part 7. Historical Perspective. How this week compares to Carrington, Miyake events and ancient peaks. The Sun has done this before. Far, far worse. On September 1st, 1859, British astronomer Richard Carrington was sketching a particularly active sunspot region through his telescope when he witnessed something no one had ever recorded: a sudden, brilliant white light erupting from the solar surface, lasting only about 5 minutes before fading. He had no way of knowing what he had seen. He had observed the largest solar flare in recorded history with his naked eye, through a telescope filter, but visible to direct vision nonetheless. Within 17 hours, the CME that eruption produced reached Earth. The aurora that night was seen across the entire planet. In the Rocky Mountains, gold miners woke up thinking dawn had arrived and began preparing breakfast before realizing it was 2 a.m. in Cuba, in Hawaii, in Colombia. The night sky burned green and red at latitudes that had never witnessed auroras before, and the telegraph networks, the 19th century equivalent of global communications infrastructure, went haywire. Operators reported sparks flying from their equipment. Some telegraph lines, disconnected from their power sources, continued operating on the geomagnetic current alone. Several telegraph offices caught fire. If a Carrington-level event struck Earth today, the effects would be orders of magnitude more damaging, because we are orders of magnitude more dependent on electrical and electronic infrastructure than the world of 1859. Estimates vary, and responsible scientists are careful to note the uncertainty. But major assessments have suggested that a Carrington-equivalent storm today could cause trillions of dollars in damage, knock out power grids across entire continents, render GPS systems unusable for days to weeks, and disable a significant fraction of the satellite constellation on which modern communications and navigation depend. This week's CME is not the Carrington event. It deserves to be said again. But history matters here, because it tells us what the Sun is capable of, and because it reveals something important about the pattern of solar behaviour. The Carrington event was not entirely isolated. It arrived during a period of generally elevated solar activity. It was part of a cluster. Records from subsequent decades show that large storms often come in sequences, that the conditions that produce one major eruption tend to persist and produce more. Then there are the Miyake events. In 2012, a Japanese researcher named Fusa Miyake, analysing carbon-14 levels in ancient tree rings from Japan and other sites around the world, discovered a sudden, enormous spike in radiocarbon production around the year 774 to 775 AD. The spike was so large, roughly 20 times above normal background levels, that the only plausible explanation was a solar energetic particle event of extraordinary magnitude, far larger than anything in the modern instrumental record, a storm so severe that it left a chemical signature in the wood of trees that were alive more than 12 centuries ago. Additional Miyake events have since been identified at roughly 793 AD, approximately 5480 BC, and around 2610 BC. They appear to recur irregularly, separated by centuries to millennia, with no clear periodicity. What they represent is the outer range of what the Sun can produce, events so extreme that they dwarf the Carrington event, the way a Carrington event dwarfs an ordinary M-class flare. Solar Cycle 25 sits nowhere near the level of a Miyake event, but the fact that the current cycle has outperformed predictions, that it has delivered elevated flare counts and stronger than expected activity during what was projected to be a moderate maximum, fits within a broader pattern of solar variability that has characterized some of the more active periods in the proxy record. Solar activity does not just vary on the 11-year cycle. It varies over longer timescales, the Gleisberg cycle of roughly 80 years, the De Vries cycle of around 200 years, and longer periods detectable in cosmogenic isotope records. Some researchers have proposed we may be in a phase of the longer cycle that favours elevated activity. This current CME, this current week, this current compound storm pattern, arriving at the equinox, it is one data point in a very long story. A story that has chapters written in telegraph office fires, in the magnetized tree rings of ancient Japanese forests, in the shocked journals of miners in Colorado who thought the sun had risen at midnight. History does not repeat exactly, but it rhymes, and right now it is rhyming with some of its louder verses. Part 8. Satellite Risk, Deep Dielectric Charging and Hidden Infrastructure Threats. Most people, when they think about solar storms, picture the aurora, the green and purple curtains of light, the night sky on fire with colour. It is beautiful. It is also the least important consequence of what a major geomagnetic event does to the systems humanity depends on every single day without ever thinking about them. The real threats are invisible. They happen in orbit, inside metal boxes spinning above the atmosphere at thousands of kilometers per hour, monitored by small teams of engineers watching telemetry screens in quiet control rooms that the public never sees. They happen underground, in transformer stations and pipeline monitoring systems, buried beneath cities and farmland and ocean floors. They happen inside the precise timing signals that coordinate the global financial network, signals so fundamental to modern commerce that their disruption would be felt within minutes in ways that no news bulletin would immediately explain. And they happen quietly, incrementally, in ways that most people never hear about, because satellite operators and grid managers do not hold press conferences every time a component behaves anomalously during a geomagnetic storm. They log it, they investigate it, and they move on because the system has redundancies and because the event was not quite bad enough to break through into public awareness. The question worth sitting with is, how bad does it have to get before it does? Deep dielectric charging is one of the most insidious of these hidden threats. The mechanics deserve full examination because they illustrate something important about why space weather risk is so poorly understood by the general public. High-energy electrons, the ones measured in millions of electron volts, elevated right now in Earth's radiation belts, have enough energy to pass through a satellite's outer metal hull. This is not a small distinction. Lower energy particles are deflected or absorbed by the spacecraft's shielding, the way a thick jacket stops rain. High-energy electrons are not rain. They are something closer to X-rays, penetrating, invisible, and depositing their energy deep inside the structure rather than at the surface. Inside the satellite, these electrons embed themselves in the insulating materials that separate electrical components. The plastics, the ceramics, the epoxies that hold circuit boards together and route current where it is designed to go. These materials were chosen precisely because they do not conduct electricity under normal circumstances. But under sustained bombardment by high-energy electrons, they begin to accumulate charge the way a thundercloud accumulates charge before lightning, slowly, invisibly, without any outward indication that anything is wrong. Over hours and days of exposure, that charge builds. The materials were not designed to store it, and they cannot hold it indefinitely. When the accumulated charge exceeds a threshold, determined by the specific material, the geometry of the component, and the intensity of the electron flux, it discharges, suddenly, in an electrostatic pulse that propagates through the circuit board with no warning and no gradual onset. The pulse can destroy transistors outright, erase memory contents, trigger false commands that send a spacecraft into an unintended mode, or permanently damage components in ways that are completely invisible from ground inspection and nearly impossible to diagnose remotely. The satellite simply begins behaving strangely, or it stops responding altogether. Satellite anomaly databases contain hundreds of events attributed or suspected to deep dielectric charging. The majority occur during geomagnetically active periods, not during the peak of individual storms necessarily, but during the sustained elevated radiation environment that follows geomagnetic activity and persists for days to weeks afterward. This is a crucial point. The danger from deep dielectric charging is not just the storm itself, it is the tail of the storm, the long, quiet, elevated radiation period after the headlines have moved on and the aurora has faded and everyone has assumed the event is over. During the Halloween storms of 2003, a period of back-to-back severe geomagnetic events in late October and early November of that year, dozens of satellites reported anomalies. One high-profile case involved a satellite in geostationary orbit that lost attitude control during peak radiation belt enhancement and had to be manually recovered by its operations team over several days of careful, painstaking work. Others simply went offline permanently, their causes listed officially as unknown or electrical anomaly, the satellite equivalent of a death certificate that reads natural causes when the actual cause was too complex or too embarrassing to specify. The total financial damage from satellite anomalies during that period ran into hundreds of millions of dollars. Most of it was never publicly reported. The satellites at greatest risk right now are those in medium Earth orbit and geostationary orbit. These are the regions where energetic electron populations are highest during geomagnetic disturbances, and they are also, not coincidentally, where the world's most critical satellite assets tend to reside. GPS satellites operate in medium Earth orbit. So do many Earth observation platforms. Geostationary orbit hosts the majority of the world's communication satellites, weather monitoring systems, and broadcast infrastructure. The overlap between maximum radiation exposure and maximum infrastructure value is not an accident of engineering. It is a consequence of orbital mechanics. The orbits that are most useful for global coverage are also the orbits that sit most squarely in the radiation belt enhancement zone. GPS satellites deserve particular attention in this context. Geomagnetic storms do not generally knock them out entirely. The satellites themselves are robust enough to continue functioning through most events. But the ionosphere, the electrically charged layer of Earth's upper atmosphere through which GPS signals must travel, is severely disturbed during geomagnetic storms. That disturbance introduces errors into the signal propagation, errors that vary unpredictably across geography, that change from minute to minute, and that standard correction algorithms are not designed to handle during severe events. During moderate to severe geomagnetic storms, GPS positioning accuracy can degrade from its normal precision of a few meters to errors of tens of meters or more in affected regions. For most casual users checking their navigation app, that degradation is an inconvenience. The blue dot wanders slightly. The turn-by-turn directions become briefly unreliable, but GPS has migrated far beyond casual navigation into domains where positional accuracy is operationally critical. A surgical robot receiving real-time positioning guidance. A precision agriculture system managing automated planting or harvesting equipment across hundreds of acres. An aircraft attempting an instrument approach in low visibility conditions, relying on GPS augmentation systems to guide it to the runway threshold. For these applications, a sudden, unpredictable degradation of positioning accuracy is not an inconvenience. It is a safety-critical failure mode. Ground infrastructure faces a separate but equally serious threat. The mechanism is geomagnetically induced currents, long wavelength, slow-varying electrical currents that geomagnetic storms drive through the conducting earth and into any long conductor that makes contact with the ground. The physics is the same as the transformer principle in reverse. A changing magnetic field induces a current in a conductor. During a geomagnetic storm, Earth's magnetic field changes dramatically and rapidly, and every long conductor on or in the ground acts as an unwilling antenna for that change. Power transmission lines are long conductors, natural gas and oil pipelines are long conductors, undersea fibre optic communication cables, which carry the majority of international internet traffic, have conducting sheaths that make them long conductors. During major geomagnetic storms, these induced currents can saturate the cores of large power transformers, the massive, expensive, difficult-to-replace devices that form the backbone of electrical grid infrastructure. A saturated transformer core causes the device to draw enormous reactive power, generates intense internal heating, and degrades the insulation that keeps high-voltage windings separated. A transformer that experiences this repeatedly, or for a sustained period, can fail catastrophically. And here is the detail that grid engineers find most concerning. Large power transformers are not off-the-shelf items. They are custom-built, they weigh hundreds of tons, and their manufacturing lead time is measured in months to years. A power grid that loses several large transformers simultaneously does not recover quickly. The Quebec blackout of March 1989, caused by a severe geomagnetic storm that lasted less than 2 minutes at peak intensity, left 6 million people without power for up to 9 hours, and caused permanent damage to transformer equipment that took years to fully address. What the compound storm pattern of this week represents, from an infrastructure risk perspective, is something more concerning than a single acute event. It is a sustained, elevated threat environment. The radiation belts have been energized for several days already, since the coronal hole stream event earlier this week. High-energy electrons are already above alert thresholds. The incoming CME will further energize that population, potentially driving it to levels that dwarf what the coronal hole stream produced on its own. And after the CME passes, after the storm index peaks and begins to decay, after the aurora fades, after the space weather bulletins return to routine language, the radiation belt enhancement will persist. Days, possibly weeks, of elevated electron flux in the orbits where the world's most critical satellites operate. Every satellite in medium and geostationary orbit will spend that entire period in an environment more hostile than it was designed to continuously tolerate. Not catastrophically hostile under normal circumstances. But the circumstances this week are not entirely normal. The magnetosphere is preconditioned. The radiation belts are starting from an elevated baseline. The equinox geometry is making the coupling between solar wind and magnetosphere more efficient than it would be in midsummer. And the source region that produced this CME has not finished erupting. The world has never experienced a truly major space weather event in the fully networked, satellite-dependent, GPS-reliant, grid-interconnected era we currently inhabit. The Halloween storms of 2003 came close to showing us what that might look like, and the damage they caused, largely invisible to the public, was significant. This week will not be the Carrington event. That needs to be said clearly. But every compound storm event of this kind is an opportunity, perhaps the most important kind of opportunity there is, to ask honestly whether the infrastructure that modern civilization depends on is genuinely ready for the one that eventually will be. Because the Sun has produced a Carrington-level event before, it has no reason not to produce one again, and the question of whether we will be ready when it does is one that this week, quietly and without fanfare, is helping us answer. Pink. Part 9. The NASA Angle, Artemis II, and Radiation Risk Beyond Earth's Shield. In approximately 2 weeks, 4 human beings are scheduled to leave Earth's protection behind. Not metaphorically, not partially, completely. NASA's Artemis II mission, the first crewed flight of the Orion spacecraft beyond low Earth orbit since Apollo 17 in 1972, is targeting launch around April 1st, 2026. The crew of 4, including the first woman and the first person of colour to travel beyond Earth orbit, will fly a trajectory that takes them around the Moon and back, spending several days in the region of space where Earth's magnetic field offers no protection whatsoever. No magnetosphere, no radiation belt filtering, no atmospheric buffer. They will be exposed to the full unfiltered radiation environment of interplanetary space, galactic cosmic rays streaming in from distant supernovae, solar energetic particles produced by flares and CME shocks, and the ambient radiation field of the inner solar system that our planet's magnetic architecture has been quietly absorbing on our behalf for billions of years. Let that sink in for a moment. Everything we have discussed in this video, the stressed magnetosphere, the compound storm sequence, the elevated radiation belts, the Russell-McFerran vulnerability, the fast-moving CME inbound from active region 4392, all of that is happening inside Earth's protective bubble. The magnetosphere, for all its current stress and seasonal weakness, is still doing its job. It is still intercepting, deflecting, and absorbing the vast majority of what the Sun throws at us. The moment those 4 astronauts cross its outer boundary, they lose every bit of that protection simultaneously. They step from shelter into open space, in the most literal sense those words can carry. Earth's magnetosphere deserves a moment of genuine appreciation here, because we have spent most of this discussion cataloguing its vulnerabilities. It deflects the vast majority of the solar wind, the continuous stream of charged particles flowing outward from the Sun at hundreds of kilometers per second. It traps energetic particles in the radiation belts and eventually clears them out through complex wave-particle interactions. It channels solar wind energy into the polar regions, where it dissipates as aurora rather than penetrating to the surface. It shields the atmosphere from the erosive effect of the solar wind, preserving the air pressure and chemical composition that complex life requires. It is, without exaggeration, one of the primary reasons that anything capable of watching a documentary about solar storms exists on this planet to watch it. The moment astronauts travel beyond it, they lose all of that, and what they enter instead is an environment that the Sun is currently making considerably more interesting than mission planners might prefer. The radiation environment in interplanetary space during solar maximum is not uniformly catastrophic. It is important to say that clearly. The Apollo astronauts travelled to the Moon and back during solar cycle 20, which was an active cycle, and none of them received radiation doses that caused acute health effects. The space between Earth and the Moon during typical solar maximum conditions is manageable with proper shielding and careful monitoring. The risk is real, but it is not a guarantee of harm. It is a probability distribution, and what solar activity does during maximum is shift that distribution toward its more dangerous tail. Orion has been designed with this in mind. The spacecraft includes passive radiation shielding, layers of material chosen to absorb and scatter incoming particles, as well as a dedicated storm shelter, a reinforced section of the vehicle where the crew can gather during periods of elevated solar particle flux. The idea is straightforward. If a solar energetic particle event occurs during the mission, the crew retreats to the most shielded part of the spacecraft, minimizes their exposure time, and waits for the event to subside. The astronauts will carry personal dosimeters that record their cumulative radiation exposure throughout the flight. 6 radiation sensors are integrated into the vehicle's structure to provide real-time monitoring of the particle environment, feeding data to both the onboard crew and mission controllers on the ground. NASA has been transparent about the radiation concern in a way that deserves acknowledgement. Agency officials have publicly stated that the mission is planned during an active solar period and that radiation monitoring will be continuous throughout the flight. The mission planning team has access to the same space weather forecast that the rest of us do: NOAA bulletins, NASA Goddard updates, real-time solar wind data from the L1 Lagrange point, and those forecasts are integrated into the day-by-day execution of the mission. The storm shelter protocol is not a last resort. It is a planned operational tool to be deployed as a matter of routine whenever the solar environment warrants it. But there is a tension in the scientific community surrounding this mission that is worth articulating carefully and honestly. Research published by solar physicist Victor Velasco Herrera and colleagues has suggested that solar cycle 25 may be in what they describe as a heightened superflare phase, extending through mid-2026, a period during which the probability of particularly intense solar energetic particle events is elevated above what a standard solar maximum assessment would suggest. This analysis is not mainstream NASA policy. It is not the consensus position of the broader solar physics community. The majority of space weather scientists would describe it as a minority view, and it should be understood in that context. But it is a legitimate scientific contribution, published through legitimate channels, and it raises a question that is not unreasonable to ask regardless of where one stands on the specific research. Should 4 human beings venture beyond Earth's magnetic shield during what is unambiguously the most active solar period in recent memory? The counter-argument is serious and deserves equal weight. Waiting for a quiet solar period is not a simple logistical adjustment. Solar cycle minima, the periods of lowest activity between cycles, last years. The Artemis program has already experienced extensive delays driven by technical, budgetary, and logistical challenges that have pushed the timeline years beyond original projections. Telling 4 astronauts, a program workforce of tens of thousands, and the international partners invested in this mission to wait for a quieter sun is not a decision made lightly or cheaply. There is also a deeper point. No solar cycle is fully predictable. The current cycle was projected to be moderate and has turned out to be vigorous. A future cycle projected to be quiet could produce an unexpected extreme event during what everyone assumed was a safe window. Radiation risk is a permanent feature of crewed space exploration beyond low Earth orbit. It does not disappear when the solar cycle graph trends downward. The question is always one of relative risk management, not risk elimination, because the risk can never be eliminated entirely. What this week's events illustrate with unusual clarity is the specific environment that Artemis 2 astronauts would be flying into and through. The CME, the active region 4392, launched on March 16th, is currently driving geomagnetic disturbance here, inside the magnetosphere, where its energy is being processed, redirected, and absorbed by the magnetic architecture that surrounds our planet. Inside the magnetosphere, the CME's effects are serious enough to threaten satellites and stress infrastructure. Outside the magnetosphere, in the space between Earth and the Moon where Artemis 2 would operate, the same CME would pass through with no magnetic field to moderate its energy. The full dynamic pressure, the full particle flux, the full magnetic disturbance, unfiltered and undiminished. Similarly, the elevated radiation belt populations that currently threaten satellites in medium Earth orbit are, paradoxically, irrelevant to astronauts operating in deep space. The radiation belts are a feature of the magnetosphere. They exist because the magnetic field traps particles. Beyond the magnetosphere, there are no radiation belts. There is something potentially worse: direct exposure to solar energetic particles that the magnetosphere would normally intercept before they could reach anyone inside it. The shield that creates the radiation belts also prevents those particles from reaching the lunar environment directly. Remove the shield, and the radiation belt hazard disappears, replaced by a different, in some respects more acute, solar particle exposure risk. The math of human space exploration has always included radiation as a line item in the risk ledger. Every astronaut who travelled to the moon during the Apollo program accepted a radiation risk that was real, if fortunately never catastrophic in any of those missions. What changes during solar maximum is not the existence of that risk, but its character. The frequency of elevated events increases. The intensity of the worst events can be higher, and the probability that a significant solar particle event will occur during any given mission window is greater than it would be during solar minimum. A 2-week mission during solar maximum is not the same radiation proposition as a 2-week mission during solar minimum, even if the average daily dose is manageable in both cases. And what this week demonstrates, with the kind of timing that makes space weather scientists check their calendars twice, is that the Sun is not coordinating its behaviour around human mission schedules. It is doing what it does, erupting, accelerating particles, launching magnetised plasma across the inner solar system on its own timeline, indifferent to launch windows, crew readiness reviews, and program milestone charts. Active Region 4392 did not consult the Artemis manifest before firing. The next region capable of producing an extreme solar energetic particle event will not either. 4 humans are preparing to leave the one natural radiation shelter our species has ever known and travel into a space environment that this week is reminding us, with considerable emphasis, is not always gentle. They are going anyway. That fact is either a testament to human courage, a calculated acceptance of manageable risk, or a question that the scientific community has not yet fully resolved. Possibly all three simultaneously. The Sun will keep erupting regardless of which answer we settle on. And in 2 weeks, those 4 people will be outside the only shield we have reading the answer in real time. Part 10. Conspiracy, Misinterpretation, and the Real Space Weather Narrative. Every time the Sun does something dramatic, a certain kind of story follows close behind. You can set a clock by it. Within hours of any significant solar event, a major flare, a visible aurora at unexpected latitudes, a published forecast for a potentially strong geomagnetic storm, social media populates with a specific and remarkably consistent class of claim. The magnetic poles are shifting and the government is concealing the timeline. The shield is collapsing and has been for years. The aurora you're seeing is caused not by solar particles interacting with atmospheric gases, but by chemical spraying programs operating at stratospheric altitudes. The Carrington event is imminent, and this time it will end civilization as we know it. Take your cash out of the bank, fill your pantry, and share this post before it gets taken down. These narratives spread with remarkable efficiency, accumulating engagement through a mixture of real anxiety, genuine ignorance of the underlying science, and in some cases deliberate amplification by accounts that have learned, through careful optimization, that fear travels faster than explanation. It would be easy to dismiss this entirely, to wave it away as the predictable noise of an information environment that rewards alarm over accuracy. But the reason these narratives find traction is not entirely irrational, and understanding why they spread is actually essential to understanding what responsible science communication about space weather requires. Space weather is legitimately complex. It involves magnetic field geometries, plasma physics, relativistic particle dynamics, and nonlinear interactions between systems operating at scales from the subatomic to the planetary. It is not intuitive. It does not map onto everyday experience in the way that, say, a hurricane does. When you explain that a coronal mass ejection is a bubble of magnetized plasma launched from the Sun's corona at thousands of kilometers per second, Most people have no experiential framework for what that means or why it should concern them. The concepts require scaffolding that a 30-second social media post cannot provide, and into that explanatory gap, simpler and more emotionally resonant stories rush to fill the space. Consider the Russell-McFerrin effect. It is a real, documented, peer-reviewed geophysical phenomenon, established in the scientific literature since 1973, that describes how Earth's magnetic geometry at the equinoxes makes the planet's magnetosphere more receptive to solar wind energy coupling. It is one of the most robustly reproduced findings in space weather research, and when you describe it to someone without context, magnetic geometries aligning at the equinox to open Earth's defences, creating a window of vulnerability that returns twice a year like clockwork, it has the cadence of fabricated mysticism. It sounds exactly like the kind of thing a conspiracy narrator would invent. The fact that it is real physics supported by decades of magnetometer data and satellite measurements does not make it sound less invented to someone encountering it for the first time, without the supporting literature, in a YouTube comment section. This is the core of the communication challenge. The truth about space weather is genuinely strange. It is strange in ways that legitimate science rarely has the platform or the communication tools to convey effectively. And that strangeness creates a permanent opening for misrepresentation. Because when the real explanation sounds almost as exotic as the fabricated one has a structural advantage. It requires no citations, it carries no uncertainty. It offers a villain, a cover-up, and a call to action, all in a format optimized for sharing. Scientists who want to convey the real, documented significance of an event like this week's CME must navigate between two distinct and equally costly failure modes. The first is over-alarm. This is the failure of describing events in language so dramatic, so saturated with worst-case framing, that the communication becomes indistinguishable from the apocalyptic content it is trying to correct. When a space weather forecaster or science communicator reaches for catastrophic language to convey the genuine seriousness of a compound storm event, they risk producing panic that is disproportionate to the actual risk, and more damagingly, they contribute to a pattern where every solar event is described as potentially civilization-ending, which erodes the public's ability to calibrate their response when a genuinely extreme event eventually occurs. This is the cry-wolf problem, and it is not hypothetical. It has measurable effects on public trust in scientific institutions. The second failure mode is under-communication. This is the failure of retreating into such measured, hedged, jargon-saturated language that the genuinely interesting and important aspects of an event fail to reach anyone outside the immediate technical community. When a space weather bulletin describes a G2 geomagnetic storm as moderate with possible minor impacts to high-latitude power systems and degraded GPS accuracy in polar regions, it is technically accurate. It is also almost perfectly designed to ensure that no member of the general public understands why they should care, or what the cumulative effect of 3 such storms in a week might mean for the satellite infrastructure their lives depend on. Under-communication does not protect the public from misinformation. It creates the vacuum that misinformation fills. Both failure modes leave the public worse off than honest, vivid, accurate communication would. Over-alarm produces a population that is anxious but not usefully informed, primed to share dramatic posts but not equipped to understand actual risk. Under-communication produces a population with no framework for space weather at all, simultaneously unprepared for real consequences and maximally vulnerable to the fabricated explanations that arrive, ready-made and emotionally compelling, whenever something dramatic happens in the sky. The honest truth about this week's solar event is that it does not need embellishment, not even slightly. The Russell-McFerrin effect, described accurately and in context, is stranger and more interesting than most invented explanations. The geometry of Earth's magnetic tilt conspiring twice a year to make our planetary shield more permeable to solar energy. That is not a mystical claim dressed in scientific language. That is actual science, and it is remarkable on its own terms. The Van Allen radiation belts and the mechanism of deep dielectric charging, high-energy electrons burying themselves inside satellite insulators and building charge for days before discharging in a pulse that can permanently destroy electronics, are more genuinely concerning than anything a social media alarmist has ever fabricated about them. The fabricated versions require invention. The The real version just requires explanation. The reality of what a Carrington-level event would do to modern infrastructure is more sobering than the most dramatic conspiracy framing, precisely because it is grounded in documented physics and historical precedent, rather than speculation. We know what happened in Quebec in 1989 during a storm that was severe but not extreme. We know what the Halloween storms of 2003 did to satellites and grid systems. We can model, with reasonable confidence, what a storm 10 times more intense would do to a civilization 10 times more dependent on electrical and electronic infrastructure than the one that experienced those events. The answer does not require embellishment. It requires only honest arithmetic, and the fact that 4 astronauts are preparing to leave Earth's magnetic shield 2 weeks from now, during the most active solar period in recent memory, at a moment when the Sun has just demonstrated its willingness to fire fast CMEs at Earth's documented annual vulnerability window, is genuinely remarkable without any amplification whatsoever. It is one of the most significant human spaceflight events in more than 50 years, occurring in a solar environment that is doing everything it can to remind us that interplanetary space is not a benign or predictable place. That story does not need a conspiracy. It barely needs a narrator. It tells itself. Responsible science communication in this environment means making a specific and difficult set of choices. It means using vivid, precise language that conveys genuine significance without tipping into theatrical alarm. It means explaining the Russell-McFerran effect as the fascinating, well-established geophysical phenomenon it is, without apologizing for the fact that it sounds unusual, and without allowing its unusual sound to become a hook for misrepresentation. It means acknowledging openly that compound storm sequences are an area of active scientific uncertainty, that we do not fully understand what happens when a stressed magnetosphere absorbs a second major impact during equinox geometry, without pretending that uncertainty justifies indifference. Uncertainty about the exact outcome is not the same as uncertainty about whether the outcome matters. It means saying clearly and without hedging that this event is not the end of civilization, while also saying clearly and without minimization that events of this character are not trivially harmless, that the infrastructure risks are real and documented, and that the gap between public awareness and actual space weather risk is one of the more consequential blind spots in modern civic knowledge. The Sun is a 4.5 billion-year-old star that produces more energy in 1 second than humanity has generated across its entire history. It ejects billions of tons of plasma at thousands of kilometers per second. It has produced events powerful enough to leave chemical signatures in tree rings that grew 12 centuries ago. It is entirely indifferent to our infrastructure, our mission schedules, our preferred timelines for geomagnetic calm, and our tendency to assume that the sky above us is stable because it looks that way from the ground. The real narrative of space weather is not a conspiracy, and it is not a catastrophe. It is something simultaneously more mundane and more profound. We share a solar system with something of incomprehensible power, and learning to understand and anticipate its behavior with honesty, with precision, and with the full weight of what the evidence actually shows, is one of the most practically important scientific endeavors of our era. Truth is under no obligation to be boring, and the truth about what is happening right now, between the Sun and the pale blue dot it has illuminated for 4.5 billion years, that truth, told plainly and completely, is more than enough. Part 11. New Radar Mapping of Near-Earth Asteroids, March 2026. While everyone is watching the sky for auroras this week, a separate community of scientists is tracking something else entirely. Not plasma, not magnetic fields. Not the invisible architecture of the magnetosphere under stress. They are tracking rocks. Specifically, they are tracking rocks that share our neighborhood in the solar system, objects whose orbital paths bring them periodically close to Earth, some close enough that the word close carries a weight it does not carry in ordinary conversation. The field of planetary defense has been transformed over the past decade by one simple but profound technological reality. Our ability to see small objects in the solar neighborhood has improved dramatically, and it is still improving. A combination of upgraded ground-based radar facilities, dedicated wide-field survey telescopes scanning the sky every clear night, and advances in computational data processing have pushed the known population of near-Earth asteroids past 35,000 catalogued objects. A decade ago, that number was roughly half as large. A decade from now, it will be larger still, as next-generation survey systems come online and begin finding objects that current telescopes are too small or too slow to detect. Of those 35,000 catalogued near-Earth asteroids, a subset are formally classified as potentially hazardous. The classification has a specific technical meaning: objects whose orbits bring them within roughly 7.5 million kilometers of Earth, about 19 times the distance to the Moon, and whose size is large enough that an impact would cause effects ranging from regional destruction to global catastrophe, depending on where and how they hit. Currently, several thousand objects meet both criteria. Most of them will never come close to impacting Earth on any timescale that concerns living humans. A small number require ongoing monitoring, because their orbital uncertainties are large enough that future close approaches cannot yet be definitively ruled out as impact scenarios. 2 objects of particular note are making close approaches around March 19th, 2026, the same week that a coronal mass ejection from active region 4392 is racing toward Earth's magnetic field. The first is asteroid 2026 FA. The second is 2026 DV17. Neither poses an impact threat on this pass. Both are being tracked with radar systems and observational networks that would have been unimaginable to the planetary scientists of 20 years ago, and what those tracking efforts are producing is not just reassurance about these specific objects, but a steady, incremental improvement in humanity's overall capability to understand and respond to the asteroid population that shares our solar system. Radar ranging of asteroids is one of the most powerful and least publicly appreciated techniques in the planetary defense toolkit. The basic principle is deceptively straightforward. A powerful radio beam generated by a large antenna facility and aimed with extraordinary precision at a target that may be moving at tens of kilometers per second relative to Earth is transmitted outward, travels across the intervening distance, strikes the asteroid's surface and reflects back toward Earth, where it is captured by a sensitive receiver. The round-trip travel time of that signal, measured with atomic clock precision, gives a direct measurement of the asteroid's distance that is accurate to within a few tens of meters even at distances of millions of kilometers. That is a level of precision that has no parallel in optical astronomy, where distance measurements depend on indirect methods carrying much larger uncertainties. The Doppler shift of the returning radar signal, the change in frequency caused by the asteroid's motion relative to Earth, gives velocity. Combined with a distance measurement, this produces an orbital determination of extraordinary accuracy. But the radar technique offers something beyond just distance and speed. When the transmitted beam illuminates different parts of a rotating asteroid at slightly different times, the signal returns from different surface regions arrive back at Earth with slightly different Doppler shifts, encoding information about the object's rotation rate and the distribution of reflective material across its surface. By carefully processing those differential returns, scientists can reconstruct a 3-dimensional shape model of the asteroid, not a photograph, but a mathematical reconstruction that can reveal the object's overall form, its surface texture, whether it has large concavities or protruding features, and whether it has a companion, a small moon orbiting the primary body. That last detail is more than a curiosity. Binary asteroids, systems where a smaller body orbits a larger one, turn out to be surprisingly common in the near-Earth population, with estimates suggesting that perhaps 15 to 20% of near-Earth asteroids larger than roughly 200 meters have companions. The presence of a moon affects the object's overall mass determination, its rotational dynamics, and its response to gravitational perturbations over long timescales. For planetary defense purposes, knowing whether a potentially hazardous asteroid has a companion is directly relevant to mission planning, both for characterization missions that would study the object up close and for any future deflection mission that might need to alter its trajectory. The resolution achievable through radar imaging is genuinely extraordinary. Objects that appear as featureless point sources of light in even the largest optical telescopes, too small and too distant to show any disk under visible light imaging, reveal themselves under radar scrutiny as irregular, lumpy, sometimes contact binary shapes. Contact binaries are among the most visually striking results of radar asteroid imaging. 2 distinct lobes joined at a narrow neck, the result of a slow-speed merger between 2 separate bodies at some point in the object's history, producing a shape that looks, somewhat improbably, like a cosmic peanut or a rubber duck floating in the void. The asteroid Arakoth, visited by NASA's New Horizons spacecraft in January 2019, displayed exactly this morphology. So have several near-Earth asteroids imaged by ground-based radar, including the well-studied object Itokawa, which was later visited by the Japanese Hayabusa mission. Why does all of this matter for planetary defense? The answer comes down to orbital uncertainty and the way it compounds over time. An asteroid's position today can be measured with some finite precision, and that precision, however good, always carries a small error. When scientists project that measured orbit forward in time to calculate where the object will be in 10, 20 or 50 years, that initial positional error grows. Small uncertainties today become large uncertainties in the future, the way a small error in the direction of a rifle shot becomes a large miss at long range. The result is that an object whose current orbit is consistent with a safe future trajectory may, with its positional uncertainty accounted for, also be consistent with a future trajectory that passes uncomfortably close to Earth, or through it. Radar measurements collapse those uncertainties dramatically. A single radar ranging session, a few hours of observation during a close approach, when the object is near enough for the radar signal to return with useful strength, can reduce an asteroid's positional uncertainty by orders of magnitude compared to what optical tracking alone provides. An object that optical observations place in a wide cone of possible future positions, a cone that includes Earth somewhere within it, can often be definitively cleared from the impact corridor with a single radar session. The cone narrows to a thread that passes safely past us. The object is removed from the watch list. The planetary defense community moves on to the next candidate. This is not glamorous work in the public perception sense. It does not generate the visual spectacle of an aurora or the dramatic narrative of an inbound CME. It is careful, methodical, iterative science, measuring, refining, recalculating, updating, conducted by a relatively small community of researchers using facilities that are chronically underfunded relative to the importance of their mission. The Goldstone Solar System radar in California and the Arecibo Observatory in Puerto Rico, before its catastrophic collapse in 2020, were for decades the primary workhorses of asteroid radar ranging. The loss of Arecibo removed a capability that has not yet been fully replaced, and the planetary defense community has been working to fill that gap through a combination of upgraded existing facilities and planning for new dedicated radar systems. The asteroid science community and the space weather community operate in almost entirely separate domains. They attend different conferences, publish in different journals, use different instruments, and think about risk on different timescales. Space weather operates on timescales of hours to days. Asteroid impact risk operates on timescales of decades to centuries. The two communities rarely have occasion to collaborate or even to share the same conversation, but they share something fundamental with each other and with every other scientific discipline represented in this video. They are both engaged in the project of understanding the cosmic neighbourhood we inhabit, a neighbourhood that is neither static nor safe, that contains objects and phenomena capable of affecting our civilization in ways ranging from the subtle to the catastrophic, and that we are only now, in this particular moment of technological history, developing the tools to monitor with anything approaching adequate comprehensiveness. The asteroids making close passes this week will reveal nothing alarming. The radar returns will refine their orbits, improve the shape models, reduce the positional uncertainties, and quietly update the catalogue that forms the backbone of humanity's still nascent planetary defense capability. While the CME from active region 4392 races toward Earth's magnetic field at over 1,200 km per second, 2026 FA traces its silent arc past us, indifferent to the storm, indifferent to the magnetosphere, indifferent to the civilization below that is simultaneously watching the auroras and worrying about its satellites, and preparing to send 4 humans beyond the only magnetic shield it has. The universe proceeds on its own schedule. It always has. The question is simply whether we are paying close enough attention to read that schedule before it surprises us. Part 12. First results from a new solar observatory, 2026 instrument milestone. For most of human history, we watched the sun with our eyes. We squinted at it through smoked glass, tracked its position across the sky, noted the appearance and disappearance of dark spots on its surface with a mixture of superstition and nascent scientific curiosity. Then we built telescopes, and the Sun revealed itself to be something far more dynamic and structured than a smooth, featureless disk of light. Then we built detectors sensitive to wavelengths far beyond the narrow band of visible light: ultraviolet, X-ray, radio, extreme ultraviolet, and the Sun revealed itself again, this time as a seething, magnetically tortured plasma environment of almost incomprehensible complexity. And in the past decade, a new generation of solar instruments has begun to see the Sun in ways that no previous technology could even approximate, changing not just what we know about our star, but what we are capable of knowing. The history of solar observation is, in a meaningful sense, the history of humanity learning that the Sun is more complicated, more dynamic, and more consequential than whatever the previous generation of instruments suggested. Every time we built a better telescope, a more sensitive detector, a spacecraft capable of getting closer or imaging at a new wavelength, the Sun surprised us. It surprised us with the complexity of sunspot magnetic fields. It surprised us with the existence and structure of the corona, the Sun's outer atmosphere, inexplicably millions of degrees hotter than the surface below it, a physical paradox that remains only partially resolved despite decades of dedicated study. It surprised us with the speed and frequency of coronal mass ejections, with the existence of solar energetic particle events capable of accelerating protons to a substantial fraction of the speed of light within minutes of a flare's onset, with the intricate wave-like phenomena propagating across the solar surface following major eruptions. The pattern has been consistent across centuries of observation. Look more carefully at the Sun, and the Sun reveals something you did not expect. The current generation of solar missions represents perhaps the most ambitious collective effort in the history of solar physics to look more carefully, and the results are beginning to arrive at a moment when they matter enormously. The European Space Agency's Solar Orbiter, launched in February 2020, has been on a trajectory that no previous solar spacecraft followed. By using gravitational assists from Venus to progressively tilt its orbital plane, Solar Orbiter has been climbing out of the ecliptic, the flat plane in which Earth and most of the planets orbit the Sun, to achieve viewing angles of the solar polar regions that no spacecraft has reached before. This matters more than it might initially seem. The Sun's polar regions are not just the top and bottom of a spinning ball of plasma, they are the origin point of the next solar cycle's magnetic field. The strength and configuration of the polar magnetic fields at solar minimum, the quiet period between cycles, is one of the primary predictors of how active the next cycle will be. The fact that solar cycle 25 significantly outperformed pre-cycle predictions is at least partially attributable to uncertainties in our polar field measurements during the preceding minimum. We were working with incomplete data, and the forecasts reflected that incompleteness. Solar Orbiter is changing that. By imaging the polar regions directly, seeing the magnetic structures there in detail rather than inferring them from indirect measurements, the mission is providing the observational foundation for solar cycle predictions that are genuinely better grounded than anything that came before. The data pipeline from Solar Orbiter is still being processed and analysed, and the full scientific return of its polar observations will unfold over years and decades. But the early results have already revealed previously unseen small-scale magnetic structures in the polar regions, refined our understanding of how the polar field reversal that marks solar minimum propagates from the surface into the corona, and provided new constraints on the models used to predict the Sun's long-term magnetic evolution. The implications for predicting the character of solar cycle 26, which will begin its rise from minimum sometime in the late 2020s, are significant. Solar Orbiter's instrument suite also includes coronagraphs and remote sensing tools that are contributing to real-time event monitoring during the current period of solar activity. The spacecraft's unique vantage point, combined with its ability to image the solar wind at distances and angles unavailable to Earth-orbiting missions, makes it a valuable node in the expanding network of assets tracking the CME from active region 4392 as it crosses interplanetary space right now. More recently, NASA's Punch mission, the polarimeter to unify the corona and heliosphere, launched in 2025 and has been returning early science data through the first months of 2026. Punch is conceptually unlike any previous solar mission. It consists of 4 small spacecraft flying in a coordinated formation, their fields of view overlapping and complementary, together covering the region from just outside the Sun's corona all the way out to Earth's orbital distance. The instrument type, polarized white light imaging, is designed to detect the faint glow of sunlight scattered by electrons in the solar wind, making the normally invisible structure of the inner heliosphere visible as a dynamic, continuously evolving pattern of flows, density variations, and propagating structures. The primary scientific goal of PUNCH is to solve one of the most practically important unsolved problems in space weather science. How do CMEs evolve during their transit from the Sun to Earth? We have excellent observations of CMEs at their source. Coronagraphs aboard spacecraft like SOHO and STEREO have been imaging CME launches for decades, providing measurements of initial speed, angular extent, and rough magnetic structure. We have excellent observations of CMEs at their destination, the ACE and DSCOVR spacecraft stationed at the L1 Lagrange point, about 1.5 million kilometers sunward of Earth, provide in situ measurements of the solar wind and CME properties roughly 30 to 60 minutes before impact. What we have never had until PUNCH is continuous observational coverage of what happens in between, the 18 to 72 hours during which a CME travels from the corona to Earth, expanding, rotating, interacting with the ambient solar wind, and potentially changing its magnetic structure in ways that completely alter its geo-effectiveness. That gap in coverage is precisely where the most important and most frustrating uncertainty in space weather forecasting lies. The southward component of the CME's magnetic field, the BZ parameter, is the single most important determinant of storm severity. A CME arriving with a strong southward BRs will drive efficient magnetic reconnection with Earth's field and produce a severe geomagnetic storm. The same CME arriving with a northward BZ will largely deflect off Earth's magnetosphere and produce a minor disturbance. The difference in outcome, severe storm versus near miss, can be enormous, and until a CME reaches the L1 monitoring point, roughly an hour before impact, we essentially cannot predict which scenario will occur. The BZ forecast is, in the current operational framework, little better than a coin flip with large uncertainty bounds. PUNCH's continuous imaging of the inner heliosphere changes the observational basis for that forecast. By tracking the three-dimensional structure of a CME throughout its entire transit, watching how it rotates, how its leading edge interacts with the structured solar wind it plows through, how its internal magnetic configuration evolves as it expands and the solar wind applies asymmetric pressure to its flanks, scientists can, for the first time, build observationally constrained models of what the CME will look like when it arrives. The BZ prediction does not become certain, but it becomes informed by something other than the launch conditions alone, which is a qualitative improvement over current practice. The CME that Active Region 4392 launched on March 16th is being tracked by PUNCH instruments right now as you watch this. Scientists are watching its evolution in real time, measuring its expansion rate, tracking its interaction with the structured solar wind ahead of it, and feeding that data into models attempting to constrain what it will look like when it reaches Earth on March 19th. Every hour of observation produces data that will be analysed not just for this event but for what it teaches about CME physics in general. Each storm the Sun produces during this era of expanded observational capability is, in a very real sense, a free experiment run by the most energetic particle accelerator in the solar system, producing conditions that no laboratory on Earth can replicate, and now finally observed with instruments comprehensive enough to extract the full scientific content of what is happening. This is the broader context in which the current storm is unfolding. We're not just watching a CME approach Earth and hoping the forecasts hold. We are watching it with the most capable suite of solar observing instruments humanity has ever assembled. Instruments that are, for the first time, beginning to close the observational gaps that have kept space weather forecasting at the level of educated uncertainty for decades. The gap between watching the Sun and understanding the Sun has been closing, instrument by instrument, mission by mission for 4 centuries. Solar Orbiter and PUNCH represent the most recent and most significant narrowing of that gap. And the storm arriving on March 19th will leave behind it not just a geomagnetic disturbance and a few nights of aurora, but a data set that will make the next CME forecast fractionally better, the one after that better still, and the one after that better again, until someday, perhaps not in this decade but within the careers of scientists currently in graduate school, The BZ of an incoming CME is a number we know before it arrives, not a number we discover when it is already too late to do anything but brace. We are not just watching the sun erupt, we are for the first time in history genuinely beginning to understand it. And the storm that is racing toward us right now is, in its way, helping us get there. Part 13. Astro AI, Machine Learning Improving Solar Storm Forecasting. The most important number in space weather prediction is one that current physics-based models cannot reliably produce. It is not the CME's speed, though speed matters. It is not the arrival time, though getting that wrong by several hours can mean the difference between a prepared grid operator and a surprised one. It is not the storm's peak intensity, though that determines how far south the aurora will reach and how many satellites will enter safe mode. The most important number, the one that determines, more than any other single parameter, whether a given CME will drive a catastrophic geomagnetic storm or largely deflect past Earth without significant effect, is the orientation of the magnetic field inside the CME at the moment it arrives, specifically whether that field is pointing southward. That parameter has a name, BZ, and for decades it has been essentially unpredictable until it was too late to do anything useful with the prediction. To understand why BZ matters so much, you need to understand the mechanism it controls. Earth's magnetic field at the side facing the Sun points roughly northward. When a CME arrives carrying a magnetic field that also points northward, the two fields repel each other, the CME's field and Earth's field push apart, and the energy of the CME largely deflects around the magnetosphere rather than penetrating it. The storm that results may be notable but is generally manageable. When a CME arrives carrying a southward magnetic field, negative BZ, the opposite occurs. Southward CME field and northward Earth field are oriented for magnetic reconnection. The field lines connect, tear and reconnect in a continuous cycle that acts like a pump, injecting energy from the solar wind directly into the magnetosphere. The ring current intensifies, particle precipitation increases, the aurora descends to lower latitudes, and the geomagnetically induced currents that threaten power grids and pipelines grow stronger and more widespread. The difference between a CME with strong negative BZ and one with positive BZ can be the difference between a G1 minor storm and a G4 to G5 extreme event, an outcome difference of several orders of magnitude in terms of infrastructure impact. Everything else about a CME can now be estimated with growing confidence. Speed can be measured from coronagraph imagery within hours of launch, with uncertainties that have narrowed significantly over the past decade. Arrival time can be forecast within a window of several hours, good enough for operational planning in most cases. Size and density can be inferred from the same imagery. But BZ, the magnetic field orientation inside the CME, resists prediction for reasons that are deeply rooted in the physics of how CMEs form and travel. The magnetic configuration of a CME is established by the complex magnetic topology of its source region on the Sun. The twisted sheared magnetic fields in an active region like 4392 store energy in configurations that determine, when they erupt, what the internal magnetic structure of the resulting CME will look like. But that structure does not remain fixed during transit. The CME expands as it travels outward through the solar wind, and that expansion changes the geometry of its internal field. It rotates, sometimes significantly, as asymmetric forces act on different parts of its structure. It interacts with the ambient solar wind and with other magnetic structures it encounters along the way, including previous CMEs, whose remnant fields still populate the interplanetary medium. By the time a CME reaches Earth, its magnetic structure may bear only partial resemblance to what it looked like when it left the Sun. Modelling all of that evolution, from source region topology, through eruption dynamics through transit physics, with sufficient precision to make a useful BZ forecast, has been beyond the capability of existing physics-based models. Not for lack of effort, for lack of sufficient observational constraints and insufficient computational resolution to capture all the relevant physical processes simultaneously. Machine learning is changing the calculus in ways that would have seemed implausible even 10 years ago. Over the past several years, research teams at institutions including the National Oceanic and Atmospheric Administration, NASA Goddard Space Flight Center, and universities across multiple continents have been training neural networks and ensemble learning models on the accumulated archive of solar observations and in situ solar wind measurements. This archive is now substantial. The Solar Dynamics Observatory, launched in 2010, has produced a continuous, high-cadence, multi-wavelength image stream of the Sun for more than 15 years, roughly 100 million individual images, each carrying information about the evolving magnetic and thermal state of the solar atmosphere. Magnetogram sequences from ground-based synoptic networks extend the record back further in time with lower cadence. Coronagraph observations from SOHO and Stereo have documented hundreds of CME launches with varying completeness. And the in-situ measurement record at the L1 Lagrange point, direct measurements of solar wind properties, including magnetic field orientation, at the point where the effects are felt roughly an hour before Earth impact, now spans multiple complete solar cycles. The goal of machine learning applied to this archive is not to replace physical understanding. It is to find statistical relationships in the data that physics-based intuition alone would not identify. Patterns that exist in the high-dimensional space of observational variables that are real and predictive, but too subtle or too complex for human analysts or traditional statistical methods to extract. Not just the obvious correlations, yes, more magnetically complex active regions produce more powerful flares, and yes, faster CMEs tend to drive stronger storms, but the subtle, higher dimensional signatures in magnetic field evolution that precede eruptions and carry information about the CME's likely magnetic structure before the eruption occurs. Early results from these efforts have been genuinely promising while remaining appropriately preliminary. Some machine learning models have demonstrated forecast skill for CME arrival times that matches or exceeds the performance of operational physics-based models, not by understanding the physics better, but by finding patterns in historical cases that correlate with arrival timing. Others have shown the first tentative ability to constrain BZ orientation probabilistically, not with high confidence, not with the precision that would allow a grid operator to make binary safe or unsafe decisions, but better than random chance. In an operational forecasting context, where the current BZ forecast is essentially a coin flip until the CME is 40 to 60 minutes from Earth, even a modest improvement in probabilistic skill is operationally valuable. A forecast that says there is a 65% chance of southward B is not certainty, but it is actionable information that a purely physics-based model currently cannot provide at all. The broader integration of artificial intelligence into solar and space physics extends well beyond CME forecasting, and the scope of what is being attempted is worth appreciating. Machine learning algorithms are now being applied to magnetogram image sequences to identify subtle precursors to solar flare eruptions, changes in the fine structure of active region magnetic fields occurring in the hours before an eruption that human analysts examining the same images would not notice. These precursors are not obvious features. They are patterns in pixel-level magnetic field evolution that emerge from the statistical structure of thousands of historical pre-flare cases and that carry genuine predictive signal about eruption probability and timing. If these precursor identification methods can be validated and operationalized, they could extend the warning time before flare events from the current near-zero advance notice to something measured in hours, enough time for satellite operators to put assets in safe mode, for grid operators to implement protective switching, for mission controllers to adjust astronaut activities in response to an elevated radiation threat. Machine learning is also being applied to the problem of historical event classification, using the cosmogenic isotope record preserved in tree rings, ice cores, and lake sediments to identify solar or cosmic events that occurred before the era of instrumental observation. The Miyake events, sudden spikes in atmospheric radiocarbon and beryllium-10 that indicate massive solar energetic particle bombardment, were first identified through manual analysis of tree ring records. Machine learning applied to extended isotope archives has begun identifying additional candidate events that manual analysis missed, potentially extending the catalogue of extreme historical events and providing better statistical constraints on their recurrence rate. That recurrence rate is directly relevant to infrastructure planning. If Miyake-scale events occur once per millennium rather than once per 5 millennia, the engineering standards for grid and satellite resilience look very different. The challenges facing machine learning in space weather are real and deserve honest acknowledgement. Extreme space weather events are, by definition, rare. The most dangerous storms, the ones where accurate forecasting would have the greatest societal value, are precisely the ones with the fewest historical examples in the training data. A neural network trained on thousands of moderate geomagnetic storms learns the statistical structure of moderate storms. When it encounters an extreme event, a storm outside its training distribution, in a regime where the physical processes may operate differently than they do at moderate intensity, its predictions may fail in ways that are systematic rather than random. The model will not know it is outside its training regime. It will produce a confident-looking output that may be confidently wrong. Detecting and communicating that kind of failure mode in real time during an event when operational decisions need to be made is a genuinely unsolved problem in the application of machine learning to high-stakes forecasting. What artificial intelligence offers space weather prediction is not certainty. That needs to be understood clearly. It is enhanced probability, a richer, more nuanced characterization of the range of possible outcomes and their likelihoods. The shift from a binary alert system, a CME, is incoming. Prepare for a moderate storm, to a probabilistic forecast that specifies the likelihood of southward BZ, the most probable timing of peak impact, and the uncertainty bounds around those estimates is the difference between a fire alarm and a weather forecast. A fire alarm tells you something is happening, and you should respond. A weather forecast tells you there is a 70% chance of rain, the heaviest precipitation will likely arrive between 2 and 5 in the afternoon, and the uncertainty is higher for the evening hours. Grid operators, satellite managers, and mission planners can act on a weather forecast in ways they cannot act on a fire alarm. The sophistication of the decision support matches the sophistication of the decisions that need to be made. The Sun fired a CME at Earth this week. It is crossing the inner heliosphere right now, carrying within it a magnetic field whose orientation will determine whether March 19th becomes a notable space weather event or a severe one. Somewhere in the data streams flowing from Solar Dynamics Observatory, from Punch, from the L1 monitoring spacecraft, from ground-based magnetometer networks, somewhere in all of that data, the pattern that predicts the next CME before it fires may already be present, encoded in the magnetic evolution of active region 4392, waiting for a model sophisticated enough to read it. We are not there yet, but we are, for the first time, pointed in exactly the right direction. Part 14. Gravitational waves from the Sun. New constraints from 2026. LISA Pathfinder data. While the world watches charged particles rattling Earth's magnetic field this week, another class of scientists is listening for something incomparably more subtle. Not particles, not magnetic fields, not the plasma dynamics of a stressed magnetosphere or the energetic electrons burying themselves inside satellite insulators. They are listening for distortions in the fabric of space itself, ripples so small that the entire observable universe serves as the detector, and the signal they are hunting is quieter than anything else physics has ever attempted to measure. Gravitational waves are, in the most literal sense possible, ripples in space-time. When massive objects accelerate, when two black holes spiral toward each other across the final seconds of a billion-year orbital decay, when two neutron stars collide in a cataclysm visible across half the observable universe, when a massive star collapses asymmetrically in the first milliseconds of a supernova, they distort the geometry of space and time around them. That distortion propagates outward at the speed of light, stretching and compressing space itself as it passes. Everything the wave moves through, every meter of space, every atom of matter, is alternately stretched and squeezed, infinitesimally, as the wave passes. The effect is real. It is physical. It carries genuine information about the events that produced it. And it is almost incomprehensibly small. The first direct detection of gravitational waves was announced in February 2016 by the LIGO collaboration, the Laser Interferometer Gravitational Wave Observatory, a pair of facilities in Washington State and Louisiana operating in concert as a single detector of extraordinary sensitivity. The signal they detected had travelled more than 1 billion light-years to reach Earth. It was produced by the merger of two black holes, each roughly 30 times the mass of the Sun, spiralling together and colliding in an event that released more energy in its final fraction of a second than all the stars in the observable universe combined emit in visible light during that same interval. That cataclysm, occurring at a distance of over 1 billion light-years, produced a distortion of space-time at Earth's location that LIGO's instruments registered as a change in the length of a 4-kilometre laser arm by an amount roughly 1,000th the diameter of a proton. Pause on that number for a moment. A proton is already fantastically small, about a femtometer, or 1/4,000,000th of a meter, in diameter. LIGO measured a length change 1,000 times smaller than that. It did so by bouncing laser light back and forth between mirrors suspended in ultra-high vacuum on seismic isolation systems of extraordinary sophistication, measuring the interference pattern of the returning light with sufficient precision to detect that sub-femtometer length change against a background of thermal noise, quantum noise, and the constant seismic vibration of the Earth beneath the detector. It was, without exaggeration, the most precise measurement in the history of experimental science. The universe was revealed to be a medium that vibrates, that carries physical information in the form of geometric distortion, and humanity had finally built ears sensitive enough to hear it. Since that first detection in September 2015, the LIGO Virgo Kayagra network of ground-based gravitational wave detectors has identified dozens of confirmed merger events, black hole mergers, neutron star mergers, and mixed systems, representing the opening of a genuinely new observational window on the universe. Events that were previously detectable only through their electromagnetic radiation, or not detectable at all, are now accessible through their gravitational wave signatures. The field of multi-messenger astronomy, combining gravitational wave observations with electromagnetic counterparts detected by telescopes across the spectrum, has already produced results that would have been impossible a decade ago, including measurements of the Hubble constant, constraints on the equation of state of ultra-dense nuclear matter, and direct observation of the R-process nucleosynthesis that produces heavy elements like gold and platinum in neutron star mergers. But LIGO and its ground-based cousins face a fundamental limitation that no engineering improvement can fully overcome. The Earth itself vibrates. Ocean waves crashing on coastlines thousands of kilometers away produce seismic noise that propagates through the ground and into the detector. Human activity, traffic, industry, the footsteps of people walking near the facility contributes mechanical noise. Geological processes, from microseismic events to solid Earth tides, add further contamination. All of this vibration masks gravitational wave signals below roughly 10 Hz, making ground-based detectors blind to an entire frequency range that contains some of the most scientifically interesting gravitational wave sources in the universe. Massive black holes in the centers of galaxies, the supermassive objects millions to billions of times the mass of the Sun that reside at the cores of most large galaxies and occasionally merge when their host galaxies collide, emit gravitational waves at frequencies far below 10 Hz. Dense binary star systems throughout the Milky Way, pairs of white dwarfs or neutron stars orbiting each other over thousands of years, radiate continuously at millihertz frequencies. The cosmological background of gravitational waves produced by processes in the early universe, phase transitions, cosmic strings, the amplification of primordial fluctuations during inflation, is predicted to fill the universe with a stochastic gravitational wave hum at nanohertz to millihertz frequencies. All of this is entirely inaccessible to ground-based detectors. Reaching it requires going to space. The European Space Agency's LISA Pathfinder mission, which operated from 2015 to 2017, was the essential first step toward that goal. LISA Pathfinder was not a gravitational wave detector itself. It was a technology demonstrator for the future LISA observatory, the Laser Interferometer Space Antenna, a proposed space-based gravitational wave detector consisting of 3 spacecraft flying in a triangular formation separated by millions of kilometers, linked by laser interferometry. The core technical challenge of LISA is keeping a freely floating test mass, a small cube of gold-platinum alloy inside each spacecraft, in as close to perfect gravitational freefall as possible, isolated from all non-gravitational forces, so that any motion of the test mass relative to the spacecraft can be attributed to gravitational wave distortion of space-time, rather than to residual atmospheric drag, solar radiation pressure, or spacecraft vibration. LISA Pathfinder demonstrated that this challenge could be met. Its test masses achieved levels of gravitational isolation that exceeded the mission's design specifications by a significant margin, better than anyone had expected, better than the most optimistic pre-flight models had predicted. The measurement validated the core technology at a level of confidence that removed the primary technical uncertainty from the LISA mission concept. The full LISA observatory, currently targeted for launch in the early 2030s, will extend the frequency reach of gravitational wave astronomy to the millihertz band, opening that entire universe of supermassive black hole mergers, galactic binary systems, and early universe backgrounds to direct observation for the first time. Ongoing analysis of the LISA Pathfinder Measurement Archive, extending through 2025 and 2026 as researchers continue to extract scientific value from the dataset, has been used to set new upper limits on various potential sources of low-frequency gravitational signals, including perturbations that could originate from solar or heliospheric dynamics. This is where the story connects, however tangentially, to the solar storm unfolding this week. The Sun is not expected to be a significant gravitational wave source in the conventional sense. Gravitational wave emission requires accelerating mass distributions, and the Sun's internal dynamics, its convective churning, its oscillatory modes, its magnetic activity cycles, are not energetic or asymmetric enough to produce gravitational waves above any foreseeable detection threshold. But the exercise of demonstrating that no unexpected signals are present in the LISA Pathfinder data above certain amplitude levels is itself scientifically valuable. It sharpens the boundary between real signal and noise, refines the calibration of the technology, and builds the analytical framework that will be applied to LISA data when the full observatory begins operations. There is a speculative dimension here that deserves acknowledgement, clearly labelled as such. Some researchers have noted that the Sun's interior, with its complex convective dynamics and the oscillatory behaviour measured through helioseismology, the study of sound waves propagating through the solar interior, which has given us our primary window into conditions below the visible surface, might in principle leave faint imprints in the gravitational wave background at very low frequencies. The solar interior is not a static object. It convects, oscillates, and circulates in ways that involve the periodic redistribution of enormous masses over timescales ranging from minutes to decades. Any dynamic mass distribution contributes in principle to the gravitational wave background. The question is whether the signal would rise above any conceivable instrument noise floor. Current analysis strongly suggests it would not be detectable with any instrument in the foreseeable planning horizon. But the fact that the question can be asked and rigorously constrained by real data is itself a marker of how far gravitational wave science has come in a remarkably short time. What this entire thread of science represents, in the broader context of this week's solar event, is something worth pausing to appreciate. Humanity currently has instruments sensitive enough to detect the stretching of space-time by a fraction of a proton diameter, caused by black hole mergers occurring when the universe was less than half its current age, arriving at Earth after travelling more than 1 billion light-years. We have instruments imaging the inner solar wind continuously from the Sun to Earth's orbit. We have spacecraft imaging the Sun's polar regions for the first time in history. We have radar systems resolving the surface features of asteroids millions of kilometres away to meter-scale precision. We have machine learning models finding eruption precursors in the magnetic field evolution of sunspots hours before the eruption occurs. All of this, the gravitational wave detectors, the solar imagers, the asteroid radars, the space weather forecasting networks, is the product of the same impulse that caused our ancestors to track the Sun's position across the sky and wonder what the dark spots on its surface meant. The impulse to look carefully at the universe, to measure what is there, to understand what the measurements mean, and to use that understanding to navigate more safely through a cosmos that is indifferent to our presence, but not, it turns out, beyond our comprehension. While the CME from active region 4392 races toward Earth's magnetic field this week, somewhere in space an instrument is measuring the trembling of space-time itself. The two endeavours feel separated by an unbridgeable conceptual distance. They are in fact expressions of exactly the same thing. Part 15. Breakthrough Exoplanet Magnetosphere Studies. We have been asking for a very long time whether Earth is unusual, not in the ways that make for easy conversation, its comfortable distance from the Sun, its liquid oceans, its oxygen-rich atmosphere, the particular cocktail of conditions that allowed single-celled organisms to eventually produce creatures capable of building radio telescopes and asking questions about their own origins. Those features have been the focus of exoplanet research since the first planet was confirmed orbiting another Sun-like star in 1995. The search for Earth analogues, worlds with the right temperature, the right chemistry, the right orbital geometry for liquid water, has driven the design of space telescopes, the careers of thousands of researchers, and the popular imagination of what it might mean to find life beyond our solar system. But there is a more subtle question lurking beneath the habitability discussion, one that this week's events make newly and viscerally concrete. It is not about temperature or chemistry or orbital mechanics, it is about protection. Does the planet have a magnetic shield? And if so, is it strong enough to matter over the billions of years that complex life requires to emerge? This question has been difficult to answer for distant worlds because magnetic fields are invisible. They produce no light. They do not transit across the face of a star in a way that a space telescope can measure. They do not imprint themselves directly on a planet's spectrum. For decades, the magnetic field status of exoplanets was simply unknown, an important variable in the habitability equation that observations could not constrain. We knew Earth had one, we knew Mars had lost one, we knew Jupiter had an extraordinarily powerful one. But for the thousands of exoplanets catalogued by missions like Kepler and TESS, the question of whether any of them possessed magnetic shields remained entirely open. Recent research, published and extended through early 2026, has begun to push toward the first tentative answers. The detection method is indirect but physically well-grounded. When a planet possesses a magnetosphere, and that magnetosphere is compressed and energized by the stellar wind from its host star, the interaction can drive auroral radio emissions, radio waves produced at characteristic cyclotron frequencies by electrons accelerating along the planet's magnetic field lines into its polar atmosphere. This is not a speculative mechanism. We observe it in our own solar system. Jupiter produces powerful radio emissions through its magnetic interaction with its volcanic moon Io. Saturn, Uranus and Neptune all produce auroral radio signatures. Earth produces them at lower intensity. The physics is established. The question is whether the signals from exoplanets are detectable at interstellar distances with current radio telescope technology. Recent observations using arrays, including the low-frequency array, LOFAR in the Netherlands, have identified several candidate systems where the pattern of radio emission is consistent with star-planet magnetic interaction rather than stellar activity alone. The evidence is not yet definitive. Distinguishing a planetary magnetospheric signal from the radio noise produced by the host star itself, which can be energetic, variable and spectrally complex, especially for the red dwarf stars that host many of the most closely studied, potentially habitable exoplanets, remains a significant technical challenge at current sensitivity levels. The signals are faint. The contamination from stellar emission is substantial. And the statistical frameworks for claiming detection versus claiming consistency with detection are the subject of active methodological debate within the field. But the direction of travel is clear. The capability is advancing with each new generation of radio array technology. The analytical methods for separating planetary from stellar radio signals are improving as more candidate systems are studied and as the theoretical models for auroral radio emission are refined against solar system observations. The first confirmed unambiguous detection of an exoplanet magnetosphere is now widely regarded within the field as a question of when, not whether. And when it comes, it will add a new column to the habitability spreadsheet, one that has been conspicuously empty since the first exoplanet was discovered 30 years ago. Why does this matter so much for the question of whether a planet can host life? The answer requires thinking on geological and evolutionary timescales rather than human ones. Earth's magnetosphere is not primarily relevant to life on the timescale of a human lifetime, or a civilization's lifetime, or even the span of recorded history. On those timescales, its main effects are the ones we have been discussing all week: deflecting solar wind, moderating geomagnetic storm intensity, protecting satellite infrastructure, reducing radiation exposure at the surface. Important certainly, but not existential, at least not for most events in most centuries. On billion-year timescales, the picture changes entirely. Without a magnetic field to deflect the solar wind, a planet's atmosphere is subject to a slow but relentless process of erosion. The solar wind, that continuous stream of charged particles flowing outward from the sun at hundreds of kilometers per second, strips atmospheric gases from an unprotected planet through a combination of sputtering, ion pickup, and photochemical processes. Hydrogen, the lightest element, is most vulnerable. And hydrogen is a constituent of water. A planet losing hydrogen to solar wind stripping is, on geological timescales, a planet losing its water, molecule by molecule, ion by ion, over hundreds of millions to billions of years. Mars is the case study. Mars today is a freeze-dried world with an atmosphere less than 1% as thick as Earth's, so thin that liquid water cannot exist stably on its surface despite temperatures that occasionally rise above freezing. The evidence for a wetter Martian past is abundant and growing. Ancient river valleys, lake beds, deltic deposits, minerals that form only in the presence of liquid water. Mars was once, in some meaningful sense, a wet world. What happened to it is a story that magnetism tells in part. Mars lost its internally generated magnetic field approximately 4 billion years ago, when its smaller molten core cooled and solidified sufficiently to stop generating the dynamo that had been sustaining the field. Without that field, the solar wind began stripping the Martian atmosphere. Over the following billions of years, the atmosphere thinned, the water disappeared, and whatever potential Mars had for sustaining complex life, if it ever had any, evaporated along with its oceans. Earth avoided that fate because Earth is larger, with a more slowly cooling core that has sustained a liquid iron outer core and the magnetic dynamo it generates for 4.5 billion years. That dynamo, that circulation of molten iron deep beneath our feet, driven by convection and the Coriolis effect of Earth's rotation, is the ultimate source of the magnetic field that this week is being battered by a fast CME during its annual equinox vulnerability. The same field that is stressing satellite operators and energizing radiation belts is the field that, over geological time, kept Earth's atmosphere intact, kept its oceans liquid, kept its surface radiation environment within the bounds that allowed the gradual improbable emergence of complex multicellular life. Earth's magnetic field is also our ongoing shield against the surface radiation environment that solar energetic particles would otherwise produce. The same particles we track this week as threats to satellites and astronauts, the high-energy protons and electrons accelerated by flares and CME shocks, would, over billions of years without a planetary magnetic shield, produce a surface radiation environment that would present significant challenges to the chemistry of life. Not necessarily insurmountable challenges, life is remarkably adaptable and has evolved under a wide range of radiation conditions. But the combination of atmospheric erosion and elevated surface radiation that characterizes an unshielded planet represents a substantially more hostile environment for the emergence and persistence of complex life than the one Earth has enjoyed under its magnetic umbrella. This brings us to what is, in some ways, the most remarkable synthesis that this week's events make possible. We have spent this entire discussion analysing Earth's magnetic shield from the inside, cataloguing its stress, its seasonal vulnerabilities, its current compromised state after a week of compound geomagnetic disturbance. We have tracked the implications for satellites, for power grids, for astronauts preparing to leave the shield entirely, for the infrastructure of modern civilization that depends on the shield's effectiveness without most of its beneficiaries ever thinking about it. And now, standing at the outermost edge of this story, we find ourselves looking outward across interstellar distances and asking the same fundamental question about other worlds that this week has made so tangible about our own. Do they have what we have? Is there a magnetic shield wrapping another rocky planet somewhere out there, deflecting its star's wind, preserving its atmosphere, moderating its surface radiation environment, quietly enabling whatever might be happening on its surface over geological time? We do not yet know. The first confirmed detection of an exoplanet magnetosphere has not yet been made. But we are closer to being able to ask the question observationally than we have ever been. And the tools being developed to answer it, radio arrays sensitive enough to hear the auroral whisper of a magnetosphere light years away, are the same tools that are expanding our understanding of Earth's own magnetic environment, of the Sun-Earth interaction that this week has put on such vivid display. The CME that left the Sun on March 16th is going to arrive at Earth on March 19th. It will compress the magnetosphere, drive ring currents through the inner magnetosphere, induce currents in power lines and pipelines, paint auroras across skies at latitudes that rarely see them. Satellites will enter safe mode. Grid operators will watch their monitoring systems. Somewhere in northern Canada or Scandinavia or southern New Zealand, someone will step outside into the cold and look up and see the night sky moving in colours they have never witnessed before. green and red and purple curtains shifting and folding across the stars, and they will not know in that moment that what they are watching is the visible face of a 4.5 billion year relationship between a star and the magnetic architecture of the world they are standing on. The Sun has been sending events like this one toward Earth for as long as Earth has existed. Earth has survived every one of them. Its magnetic field, battered and stressed, and seasonally vulnerable and imperfect in the ways we have spent this entire video documenting, has been enough. More than enough. It has been, over billions of years, the silent prerequisite for everything that has ever lived here. Every organism that has ever drawn breath, metabolized sunlight, reproduced, evolved, or looked up at the sky and wondered what was out there. All of it has occurred inside the shelter of this invisible, magnetic architecture, under the protection of a field generated by the slow circulation of molten iron in the darkness 3,000 kilometers beneath our feet. What we are only beginning to understand by turning our instruments toward distant worlds and asking whether they too are protected is how extraordinary that shelter has been, how specific, how contingent. How much of what we are and what we might yet become depends on a magnetic field that most of us have never thought about for a single moment of our lives. The Sun picked its moment this week, it always does, and Earth, as it always has, will hold.